So what we talked about on Tuesday was, first off, that we can get an enolate, or get the enol or enolate. So that's kind of why that chemistry has been centralized in the middle of this. So we can either go to the enol form or the enolate form. Realize that as far as this chapter goes, pretty much everything is driving through the enolate. Okay, why would we expect the enolate to be our predominant source over the enol?
Negative charge?
Yeah, it's a better nucleophile. We've got that negative charge. So with that, we can get it to be more reactive, a little bit easier to manipulate. There's less equilibrium dynamics, so we can help kind of push things along a little bit smoother under base conditions. We looked at reacting it with bromine as our electrophile. Okay, so this is, again, going to become more and more important. You have to be able to identify how each of these species reacts. When we're looking at bromine, it's a good electrophile, fairly large, easily delocalizable electron cloud. When we get it near either our base or our acid, we can polarize it enough and get it to act as an electrophile. Okay. So our enolate or the enol can come in, react with the bromine, and we end up doing a substitution reaction for one of the hydrogens off of the carbonyl compound. Depending on those conditions, if we run under acidic or basic conditions, we see differing results. So both the drawings here show the exact same result. However, you have to realize that under basic conditions, we won't see monosubstitution. And that's because we have a much stronger nucleophile. That stronger nucleophile, and secondarily, it's still the nucleophile. Once we put on one bromine, we've now made our nucleophile even more nucleophilic because that bromine starts to draw electron density away, making that one of the other hydrogens even more acidic, and that can be pulled off even quicker. Okay? So we won't see monosubstitution when it comes to the base reaction. We take advantage of that base reaction at the very top. That's our Haloform test. You will undoubtedly see that show up as an ACS question. Okay? It seems to be one of their favorite questions. I remember way back when I took it, I was surprised, I had no idea what the heck they were talking about. Try and process through some of those pieces. Okay? If you're starting with a base, you've got that acidic hydrogen on your alpha carbon. With that could potentially react with your halogen, and we can propagate that further along. Okay? The big thing that's different when we're looking at the Haloform test, I know it's really not easy to see. Let me shift one of these projectors temporarily so we can see it a little bit better. We start with a methyl ketone, and we end up converting it into a carboxylic acid. Okay? What ends up happening is we turn that methyl group into an exceptionally good leaving group because of all the bromines. Okay? That can then act as a base once it's removed, can pull off the hydrogen. We have to follow that reaction up with an H3O plus to fully acidify. Okay? And I'm pretty sure that's what our next slide is. No, I lied. Okay? So this actually went back a little bit. This is looking at our base conditions. We can pull off that hydrogen. We form our nucleophile, can react with our electrophile of our bromine, and we've done our substitution. Okay? Remember that bromine polarizes the bond, as we just talked about, which makes that carbon more positive. So it starts to freak out and take electron density away from the hydrogen, and we can get our reaction to occur a second time. And we do a second substitution. So once we've done a single substitution, it becomes even more acidic, and then we've got to watch out for that chemistry, okay? Which means we do not see that monosubstitution. The example that we were just talking about with methyl ketones, that's where we see this big effect primarily when we're looking at bromine as our electrophile. So we still have that acidic hydrogen that can be removed by our base. We form our resonance stabilized enolate. The enolate reacts with bromine, and we can do a single substitution. The issue is that carbon is now even more acidic, so it loses yet another hydrogen, and we continue to do this until we have 3 bromines on there. Those 3 bromines, all being extremely electron withdrawing, can polarize that carbon into a really good leaving group, can take the electrons away from our other carbon, and our result, sorry, that was drawn kind of weird, is this guy with now CBr3, the negative charge. Okay, that is a pretty good leaving group, and we have a pretty good carbocation as far as stability goes. Why is that carbocation relatively stable? What's its fancy name? It's the acylium ion, which I may be misspelling there. Okay. Do we have a good source of electrons in that solution? We still have our strong base. Okay. The hydroxide, instead of acting as a base, can act as a nucleophile. We can end up with our carboxylic acid functional group. But then again, we have to realize that that is very acidic, and we have that carbon tribromide compound floating around, which is extremely basic, can pull that hydrogen off, and we'd end up with the carboxylate salt. To get our acid back, what do we have to do? We'd have to follow our reaction up with acid, which is why when we run this reaction, it's 2 steps. The second step is to add the H3O+, and that gets us to our final answer, okay, the carboxylic acid. Okay. Definitely shorthanded a lot of that mechanism. Are there any questions about it? Yeah.
So if you pull off one of the methyl groups on the other side and replace it with a hydrogen, will it go through everything, get the OH on the side, and then again have the bromine intact, the hydrogen on the other side?
Putting a bromine on the other side. There is a potential for that, and I think it probably won't because you've generated the carboxylic acid. And the acid is going to neutralize your base, which reduces that chemistry. And I don't think I've got this on another slide. Let me check real quickly. No, I don't. If we go all the way back to the very beginning, maybe. We've got the Hell-Volhard-Zelinsky reaction. If just base and bromine worked to do that substitution with a carboxylic acid functional group, I would expect that's what we would use. Okay? When you look at that reaction, we aren't using just those reagents. So I have a feeling that that carboxylic acid functional group changes the chemistry enough around the alpha position that it's not going to work under those basic conditions.
Because I think Sapling had it where it actually put the bromine on the other side, but I didn't understand why.
I'd have to take a look at it to see a closer look. Most cases, when I've seen the Haloform test, what they're looking at is just making the carboxylic acid. In fact, even in the summary slide, you can see that up at the top. We're not putting on a bromine on the other side of that. It's just taking it to the carboxylic acid. So yeah, if you can tell me what question that is, I can look at it in lab, figure out what's going on with that. Okay. So that is bromine as an electrophile. Okay, as I kind of alluded to already, I have seen this kind of question show up on the ACS test. They may not ask with bromine, they may ask with iodine. Iodine is a more common one because the yellow solid, or the leaving group, Ci3, which is then your good base to remove the hydrogen, that compound right there has very low solubility, and you can see it precipitate out of solution. So it's something that is typically used to identify functional groups. If you have a methyl ketone, you can add the base and elemental halogens, and you'll see this precipitate. If you see that precipitate, then you know you have a methyl ketone. Okay, so it's a standard classification test for the presence of a methyl ketone. Okay, so more than likely what they would do is give you A similar type question is what's written here. What type of structure or which of the following structures would give a yellow solid when mixed with iodine and sodium hydroxide? What they're really asking for is this haloform test. Okay? We can make it more specific to whatever halogen we were using. So more than likely you'd see it as the iodoform test, okay? Because iodine is being added instead of bromine. Okay? Questions about that one? Okay. So what we're going to start to shift into now is all or some of the other electrophiles that we could work with. Carbon as electrophile is reasonable. Okay, we've seen that before. All we have to do is attach it to something that's electronegative, like a halogen. Okay, so what we're going to do to get our carbon electrophile is what's shown in step 2 of this reaction. Okay, so that gives us our electrophile, but for our reaction to work, what do we need? What do electrophiles react with? Nucleophiles. Okay, if we're going to put the R group here, where does our nucleophile atom or nucleophilic atom necessarily have to be? That alpha carbon. How can we get the alpha carbon nucleophilic? Remove a hydrogen. Okay, which means our very first step of the reaction, our alpha carbon must act as what? Acts as an acid. If it acts as an acid to make it a nucleophile, what does it need to react with? A base. So our very first step is ultimately to make our nucleophile, and we're going to do that by adding a strong base. We could add something like sodium hydroxide or a basic alcohol, some kind of alkoxide group. The issue with that is we don't generate a large percentage of our enolate ion. So we really want to maximize the reactivity. So what we want to do is use a base that is going to completely remove all hydrogens from our compound. Okay, remember we had 3 bases, the alkoxide, sodium hydride, and then LDA. Sodium hydride and LDA would both work. Why do we tend to favor LDA? Remember that one? What was that? Say that again. We could make a safety argument against it, or for it. The hydride would generate hydrogen gas. Okay, if we're heating our reaction, that could be a bit dangerous. I think the bigger issue for why we use LDA is it's soluble in organic solvents. The sodium hydride much, much smaller. So while it does do a good job pushing our equilibrium towards our enolate, its very low solubility means that we can't actually get it to react as efficiently as if we used LDA. LDA has those large alkyl groups. Those alkyl groups help stabilize or help solubilize the compound, which allow it to act as a base. Okay. Any other ideas why adding the alkoxide would be a bad idea? Let's draw up some structures here. So our LDA was this guy. Why is adding an alkoxide also going to be a bad idea? So let's choose methoxide. What was the point of our base? What was its role? Remove a hydrogen to do what?
Make the carbon more nucleophilic.
Make our nucleophile. What charge does our nucleophile have? A negative. What charge does our base have? Negative. If we add a base, what are we also adding? A nucleophile, which could potentially mess with the reaction. Okay? We want only our carbon nucleophile. If we take a look at our LDA versus our methoxide, which one can act as a nucleophile? Methoxide. Why can LDA not act as a nucleophile? No, we would still see a cation to stabilize our methoxide. What's that? Yeah, steric hindrance. Those large alkyl groups on our LDA will neutralize its ability to act as a nucleophile. It is sterically hindered. So it can really only act as a base. Okay? That can facilitate the removal of the hydrogen. We could then go through and put in our electrophilic halogen or alkyl halide compound as our electrophile, and we could do our final substitution. So we've got some big reasons why we want to use LDA. We want to fully generate our enolate, and then we also want something that's not nucleophilic. We don't want that to impede our reaction. Okay? We would expect an SN2 type reaction. Why SN2 and not SN1? Why would it be one step? So we haven't even shown a mechanism here, so why would you expect one step? It's SN2 because it's an SN2. Interesting. If it's a strong base, that would suggest elimination, not substitution. But you got the right idea. It's a strong nucleophile. Strong nucleophile pushes our SN2 type reaction. Okay? We do have that strong nucleophile in our enolate ion, so that's why we would expect that SN2. Okay? There are some complications along these lines. If we generate that carbon nucleophile, we do have a negatively charged carbon, which means not only can it act as a nucleophile, but it could also act as a base. So once we've generated it, yes, we want it to react in that substitution reaction. But what if our alkyl halide is secondary or tertiary? All right, well, what's the issue there? We now start to sterically hinder that position. Well, if we're running under an SN2 reaction and our electrophile is sterically hindered, how else could it react? If we don't, yeah, there it was. We get an elimination reaction. So instead of acting in a substitution type fashion with our sterically free positions, what we end up having is now we got to find something to stabilize that negative. We'll pull off a hydrogen. It's a little bit more accessible. The process of pulling off that hydrogen, we've now acted as a base, and we're pushing the elimination reaction. So when we go through and do our carbon electrophiles, we really want to make sure that the alkyl halide we're using is primary, okay, which will help push that SN2 mechanism, because least steric hindrance around our alkyl halide. Okay? If we put in our secondary or tertiary alkyl halides, they now start to become so sterically blocked that instead of seeing the SN2, we start to see the elimination mechanism take hold. So when we're going through and trying to decide on an individual synthesis and we want to put on an alkyl group, we really want to make sure that what we're using for our electrophile is something sterically unhindered, so primary alkyl halides. The other issue with our LDA, we have a high concentration of the carbonyl left over. That's what we talked about with the methoxide. Okay? If we don't completely push across, we're now opening ourselves up to intermediate chemistries. Okay? So we really want to kind of push that to the extreme, get rid of all of those intermediates, and only set us up with one possible reaction site. Okay? Probably one of the largest issues with the alkylation at your alpha position is that they are very, very susceptible to polyalkylation. Okay? Why would that be the case? We don't necessarily even have to have two alkyl or two alpha carbons. Once we've done a single alkylation, why would we expect our alkylated product to react more?
There are more hydrogens that are just as acidic.
There's actually less hydrogens on that structure. So our starting has 4, right?
I don't mean more than the first one. I just mean even after that, there's still more to take off.
True, there is still more to take off, but we could try and limit that by controlling our reagents very, very carefully. What we're saying by polyalkylation is a legitimate problem is that we can't control that very well. If we set it up, we almost exclusively see the product of a single monoalkylation react before our starting material. Why does this species react before? For it to react, what does it have to become? It has to become the nucleophile. To become a nucleophile, what do we have to do? We have to remove a hydrogen. With our starting material, it doesn't really matter which one we pick, so let's just go ahead and pick any one of them. Okay. That goes through resonance, and we end up generating our resonance stabilized enolate, right? What happens with the other one? Are all the hydrogens the same? No. Which hydrogen is removed? Okay, there's 3 alpha hydrogens, but you're right. Why the left? So we'll call it purple, call it orange. If we did purple, you're right, we get less steric hindrance. But if we go to our enolate, that's what we get. If we look at, sorry, that's not a resonance arrow. If we look at our orange one, what does our enolate look like? What was that? It's more substituted. What does that mean? It's more stable, which means it reacts first. So we would preferentially see the hydrogen, our orange hydrogen, get removed before our purple. Why does that become important when we look at our polyalkylation? What is the orange one competing with then if the purple one's not there? Our red starting material. Which of those is preferred? Orange or red? Orange. Again, because of that more substituted double bond. What does that end up meaning? That means as soon as we alkylate it once, we've generated now a more reactive enolate species that's now going to react further on, and we're going to see polyalkylation. We're going to see more alkyl groups go onto that carbon, as opposed to going back and finishing out the rest of our starting material. Okay? So it's a big issue when we're trying to alkylate our carbonyls. There's a couple ways that we can get around it. We can try and limit the individual reagents to try and expose that. We can also run temperature changes. What we're looking at here is the thermodynamic versus kinetic products. So we could try and play with our temperatures and limit the possibility of our thermodynamic stability. How would we limit our thermodynamic product? Let's see. I always have to think about this one a little bit. What we're looking at is our reactants going over to our thermodynamic product versus if we had a kinetic product. What could we do? Catalysts will drop our activation barrier, but that's still going to affect, we're still going to have our kinetic product be favored. If we go to high heats, what's going to happen? We're going to provide enough energy that we're going to clear the activation barrier for both reactions. Which one's going to be preferred in that case? Lowest energy or higher energy products? Lower energy. So how can we prevent our thermodynamic product? Keep it cold. If we keep it cold, now what we're doing is only providing enough energy to hopefully clear that kinetic product level. We don't give it enough time to be able to shift up to the higher energy state. Okay? So if we want to prefer our kinetic product, we can limit the amount of heat that we put into the reaction and hope that we can push our kinetic. Okay? That's kind of a crappy way to go about things because it's really going to depend on the difference between those two. If it's a really big difference, sure, dropping the temperature is going to help us out a lot. If we don't see a huge difference in that activation barrier, we're probably not going to be able to do much with the temperature. Okay? The other way that we can limit it is we can go through and change the characteristics of our enolate. Instead of being an enolate, maybe we can change that oxygen to something else, say like a nitrogen. Okay? Whoops, which we haven't quite done yet. The next issue is regioselectivity. If we wanted to go through, and we will address actually both polyalkylation and regioselectivity in the next section here. As soon as we've gone through and put on a substituent, what we would expect is to keep putting on our carbon at that exact same position. Okay, we can't get it to go to the other side. We can't get it to balance out. Okay, so if we're going to go through and polyalkylate, we would expect our air on this carbon or on this structure. We're going to react this, turn this into an enolate. So step 1, enolate or enolize. Step 2, put on an R group. Where would that R group go? The same alpha carbon that has the R group already. Good job. Okay, we would expect it to go out there. Okay. Why? We generate that more stable intermediate again. Okay. So we lose some of our ability to actually put carbons at different positions. Okay. We can address, oh no. I totally must have changed the sequence of my slides. That's obnoxious. Okay, well, we're just going to have to trust that somewhere or another I brought back how we fix some of those issues. When we look at our regiochemistry, what we're looking at is where do we put that double bond, okay, which was the same issue that we had with our polyalkylation. Where does our double bond go? Okay. Which product would we expect to be favored, our left or our right? Why do we expect left over right? Because of Zaitsev's rule, we form the more stable or more substituted double bond. If we try and partner this back to kinetic versus thermodynamic, which one's the kinetic, which one's the thermodynamic? Kinetics on our right, thermodynamic is on the left. Okay, a couple ways that you could approach that. If you're going through and ranking based on stability, stability is always going to be a thermodynamic argument. Okay? If we're going to go through and look at speed, that's where we get in with our kinetic. So if you think about what's easier to do, easier is going to be a kinetic argument. And what do you mean? What do I mean by easier? Why is it easier to pull off the red hydrogens? There's less steric hindrance. There's also more of them. So we could make a kinetic argument in that case. If we look at our blue hydrogen, okay, that is sterically blocked, not easy to get access to. If we pull off that hydrogen, we also have a tertiary anion, which is a very unstable intermediate. Hence our activation barrier goes up a whole lot higher. But once we've got that formed, we can now form a very stable double bond because of that multi-substitution. And so now the energy of our product goes through the floor, and so we get a thermodynamic favoring there. Okay, so what we're trying to do is evaluate how those changes in the reaction affect the overall energy and dynamics of each of those reactions. Kind of makes sense? Okay. Another way to look at it, these old slides? What the heck? We could look at our energy diagram, which we also already drew up. Okay. When we look at our kinetic, we're looking at a lower activation barrier. Okay, that's why it can happen faster, because we have less stuff preventing it. If we look at our thermodynamic product, we have lower energy of our product, but a higher activation barrier. Does the thermodynamic product always have to have the higher activation? That was a bad question. Is our thermodynamic product always not our kinetic product? I don't really like that question either. Can they be the same thing? Can our kinetic product and our thermodynamic product be the same? Yeah. Yeah, they can, in theory, be the same thing. All we're saying is that our activation barrier ends up being lower as well.
In this
Okay?
case?
In this case, no.
Okay.
Yeah. In this case, no, they have to be separate. We're looking at two separate cases. What I'm trying to say is that you won't always necessarily see this. They can come out to be the same thing.
But with polyalkylation?
With polyalkylation, they're going to be different. Okay. If our thermodynamic and our kinetic products were the same thing, any ideas on whether that would be a good reaction to run or not? Yeah, it should be a really, really good reaction to run. Why? It's fast and easy is a nice way to put that. Okay. We would expect effectively one product. There isn't a competing side product, which means we get, in theory, a very high yield of one product. Okay. That's a really good thing to have happen. So in a lot of the reactions that we would run, we would hope that we get both the kinetic and thermodynamic product, okay, coming out to be the same thing. If they're different, that's where we run into issues that we try to adjust by changing the dynamics of the reaction, change the reaction conditions, change temperature, okay, change the bases that you're using. Try and adjust and push one of those completely out of the picture. Okay? Oh, I think this is where I talked about it. So when we go through and look at this one, I'm not quite sure I buy this argument, but this is what your textbook was putting forward. LDA is a strong base. Sodium hydride isn't quite as strong a base, and we can potentially reverse the reaction using sodium hydride. What's kind of the issue, or why I kind of don't like that theory? What's the conjugate acid for both of these? For LDA, it's our protonated amine. For sodium hydride, it's H2, or hydrogen gas. What's the problem with hydrogen gas? It's a gas, and it's going to leave the reaction. So, yeah, if we can provide enough heat, we could, in theory, reverse the reaction. But what happens to the solubility of a gas when you heat it up? Becomes even less soluble. So there's this huge driving force to remove that hydrogen gas. So I don't really fully believe their theory here. Theoretically, yes, that's true. Beyond that, experimentally, it's pretty useless. Okay? So what you'd be expected is we'd be using LDA, and then we would have to try and push or just kind of accept our weaknesses. Okay? This... I wonder what I did with it. I must have used the wrong slideshow somehow. Okay, so necessary reagents to make the following compound. Okay, use 5 carbons or less. So what we want to try and go through and do is see if we can identify what bonds were made or broken to try and put this compound together in the best efficiency possible. Okay, any ideas? No ideas? We're looking at the chemistry around what position? Our alpha carbons.
So we just add some base.
Base with what? So you got the right idea.
We'll take
Step 1, we probably need LDA.
then with your RX, have your R groups be, methyl.
Okay, so here's the issue though. What is our R group? And what are we starting with? We want to maximize our yield. So we want to make sure that we pick a structure that's going to allow for this reaction to happen as effectively and efficiently as possible. Okay. So pick a starting material that has 5 carbons. Which one do you want to look at? Okay, so you're picking
Basically the incomplete ring.
that. 1, 2, 3, 4, 5.
Where you have alpha carbons that are less sterically agreed.
All right, we got alpha carbon here and here. Is that what you're looking at?
Yeah.
Okay. What was that?
Why not the long chain?
What happens if we do the long chain? How many carbons?
Oh, starting
6. So we can't start with 6 carbons. We'd have to pick 5. Okay. Why include that, what I would argue is the ethyl hanging off. Why not start with the methyls on there? Why not start with something like that? What's that? So yeah, what we're looking at is trying to, what happens about the dynamics of that chemistry, what changes around each of those positions. So what we're hoping to look for is what are all the possible ways. So we are looking at trying to make any number of these 4 bonds. So what we would have to do, break it apart and try each of those and see how it affects. Okay, what your end result ends up coming out to be. 1, 2, 3, 4, 5. Oh yeah, that is 6. So one of the things that I find kind of frustrating on this one is what are we going to have to rely on? We're putting our R groups at which positions? Same side of the double bond, or the same alpha carbon or different alpha carbons? Different alpha carbons, which means what are we going to have to do? Remember when we talked about it? Yeah, we're going to have to play a temperature game on this. We have to keep our reaction cold. We're looking at this situation. We want our alpha carbon, or our carbons, to go on opposite sides of that ring. Okay? So we're going to have to be very, very careful with our temperature when we run this reaction. If we aren't watching our temperature, what's going to end up happening is we'll put all of our carbons or all of our chains off of one of those carbons, okay, which isn't a good option. So as far as this goes, I think I would break it the way you were suggesting there, Josh, as well. Try and get as many carbons as possible into the structure at first. Okay, so get the 5 carbons that way. Then how do we want to react this? We're now looking at putting on this group, whoops, that was horribly drawn, and then those 2.
Would you start with the 2 methyl?
Okay.
Down to the same side, you keep it warm first, and then you cool it down.
So we could do our methyls, our methyl halides. What base would we use? Okay, what happens if we use LDA? Which position would be, and our temperature? Cold or hot?
You don't have to have them.
Okay. If we go hot, what happens? It's the reverse of what we're seeing here. So where would it put the R groups?
The same side.
On the same side, okay? At the most substituted position. Which was most substituted? Oops, whoa, come back here. Our left was more substituted. Since we want it to go the other direction, to put on the methyls, whoops. Okay, we're gonna have to be very, very careful with our temperature game on where our individual positions go. Okay, so if we went hot first, what would we expect to go on first? We would probably put something out on this carbon. Okay, because hot's going to favor your thermodynamic product. We want the more substituted double bond. So if we're going to run hot temperatures, the R group is going to be, I'm bad at spelling, it's not spelled out. We would expect our propyl halide. If we ran with cold temperatures, okay, we could now get it to go to our kinetic product, which would be the opposite side. That's going to put on our methyls. Okay. Kind of get the idea? So it's playing back and forth a kinetic versus thermodynamic game. I doubt the ACS test would ask you something like this. I will ask you something along these lines, but going back to the energy diagrams. Okay? Evaluating the differences between these, what's your thermodynamic product, what's your kinetic product. Okay? Trying to dance between those two. A full-on synthesis problem, expecting you to go back and forth between them, that's a bit more advanced. Okay? Does that kind of make sense? Questions? Okay. Still not quite sure where my enamine went. We have another version of our carbon alkylation or our carbon electrophile. This one gets a special name. It becomes the malonic ester synthesis. Okay. Any ideas why it would get its own special name? What's the difference? And our last reaction, what was our starting material? We had a ketone with an alpha hydrogen, right? At our alpha position. Do we have a carbonyl with an alpha hydrogen in this case? There's a carbonyl. There's an alpha position. What's at that alpha position? We still have that alpha hydrogen. Why is this one getting its own special name?
It's effectively two hydrogens, two carbonyls.
We have two carbonyls, which means what about the acidity of that hydrogen? Becomes much more acidic, which means what about the base? You can use a weaker base because our hydrogen just became much more acidic. So we've changed the dynamics of the reaction by changing both the acid we were starting with and consequently the base. And apparently that is deserving enough to go through and call it a whole new separate reaction. Okay? It's not quite true. There are some other things that stand out that make it kind of neat. Okay? So what we're doing in that first step is effectively the exact same thing as we just did. Okay? You're looking at a standard alkylation with your carbonyl alpha hydrogens. You remove that hydrogen with a base, you put on the alkyl group, and now you have your alkylated species. Okay. Why else is it called the malonic ester reaction? Anybody have any idea what the name of this species is? It's a malonic ester. Okay. So if we remove that and turn it into the acid, it becomes malonic acid. Okay. We're calling it the malonic ester because that's effectively what this is. Those two carbonyls change our alcohol or our alpha carbon chemistry substantially. It has one extra happy effect. If once we've generated our now alkylated product and we go through and add acid, what is the acid going to do? I know what it looks like it's doing there, but let's slow that down a little bit.
Does it add an H to the other oxygen and make the double bond?
It'll add a hydrogen to our oxygen. So one of our oxygens picks up that hydrogen. Okay. What's the issue with that oxygen?
Too many bonds.
Too many bonds, so it's positively charged. What's it do? Acts as a great leaving group, and we can end up converting our diester into a diacid. Okay, so that's step one. We get it into the carboxylic acid form. So our R groups are now no longer R's, but we have hydrogens. Okay, well that's still not all that exciting. All we did was did a ester to carboxylic acid, acid-base conversion. That's pretty boring. What was step two? We add heat. Okay, well, the chemistry of that alpha hydrogen, which we still have some chemistry associated with that, we now have some interesting stuff that can happen. When we add that heat, what happened? What's one of our products? CO2. Where did that CO2 come from? Okay. We took the electrons away from the hydrogen, formed a carbon-oxygen double bond. What's the problem with that carbon now? Too many bonds. So it says I need to get rid of some electrons. What does it do? Shuttles these electrons over to here. Now how many bonds does that carbon have? Too many, so what does it do? Shifts the electrons up. What we end up generating is an enolate intermediate that can then go through and react oops, that's a typo. That's a hydrogen out there. Okay. React in the presence of water to generate our carboxylic acid back. Okay, or sorry, not our carboxylic acid, we have that. Get back to our alkane structure. Why would this reaction occur? That's seemingly an awful lot of arrows. What do we end up generating in the process of this reaction? Yeah, CO2. Okay, so the gas does a couple things for us. What's the entropy of a gas? High or low? High. Entropy of gas is extremely high. So this reaction is entropically favored. Okay, taking a step further, what's the stability of CO2? It's really, really, really stable. How can we prove that based on our own knowledge? What's one of the most modern current hazards that we've been dealing with in our society? Greenhouse gases, including CO2. If CO2 wasn't incredibly stable, would it be an issue? No, because we would have converted it to something else and we wouldn't be worrying about it now. CO2 is something that is very, very stable. So we end up seeing this large driving force to kick out that CO2 molecule. So this is kind of neat because we now started with an ester and we end with a carboxylic acid, and in the process we've now added some carbons to an extended structure. Depending on what we're looking at starting with, okay, most people tend to focus around the malonic ester or the malonic acid, but we could go through and change our view and say we were looking at that R group. Okay, what happened to that R group's structure in the course of this reaction? What did we add to it? We added 2 carbons, including a carboxylic acid as part of that. Okay, so we actually made our carbon chain longer by 2 carbons and also made it a carboxylic acid functional group. Okay, so it's kind of a big change as far as the overall structure goes. Okay, that big piece change is ultimately one of the big reasons why we would use the malonic ester synthesis, okay, or malonic ester alkylation reaction. Okay. If we break it down into individual mechanistic steps, what's shown below is your very first step. We're still forming our enolate. We're pulling off that hydrogen, forming the enolate nucleophile. Our carbon is now very nucleophilic, so we can react it with something electrophilic. What's our electrophilic atom? RRX. What can happen? Pick out our X, and we now have the R group attached. Okay. Once the R group is attached, we now have a couple different options that we could go through. Okay. We could go through, up as we did at the very top of this, go through and add our acid and our heat, and go through and end up with carboxylic acid. Or we could evaluate the chemistry about this group a second time. Do we still have an alpha hydrogen? Yeah. So what could we do? We could do it again. We could remove that hydrogen again. Again, we have to use a strong base, and we can now put on yet another R group. Okay? It could be the same, it could be different. It ultimately doesn't really matter. Okay? So we could end up going through and now pretty much drastically changing our carbon chain length, all focused around relatively simple chemistry. Okay? So it's kind of a neat reaction in that case. Okay. So we can see the result there. This is where we're looking at our hydrolysis. When we add that H3O+, it'll react with our oxygens. Okay. Pick up a hydrogen. We end up with our positively charged oxygen. That is now an exceptionally good leaving group. We're in the presence of H3O+, which means we also have water. What's special about water? Lots of things. What's the lots of thing that's going to be important in this case? Could act as an acid or a base, but that doesn't really change our chemistry. Just maintain the same structure. It's a good leaving group, but it's already left. What's special about the lone pairs? They can act as a nucleophile. We can attack that carbon. Carbon can now shuttle off those electrons to our good leaving group in our ethanol. And what we end up doing is making our carboxylic acid functional group. I know, our alcohols are all sorts of fun. We can run through a billion different chemistries. Okay? So the trick is to try and apply that chemistry back to each individual reaction. So our oxygen can act as a good nucleophile, kick that guy out, and we end up with our carboxylic acid functional group. We can run this twice to fix both of our esters, and we end up with that species. Okay? That species is inherently unstable, okay? And we can do some internal acid-base chemistry, and in the process of that, we can kick out CO2 as a reasonable good leaving group. Okay? That whole chemistry is driven by the stability of that intermediate. Why is this intermediate stable? What is special about what I just circled? That is known as an enol. That enol can tautomerize and take us back to the carboxylic acid. Okay? So we're taking advantage of multiple forms of chemistry in this reaction to go through and set us up. How come we can't remove that second carboxylic acid group? Do we have a second enol to tautomerize? No. Without that enol formation as an intermediate, we cannot remove the carboxylic acid. Okay? So if we tried to, say, take the electrons across, whoops, we could kick that pi bond out, but ultimately what we want is to push the electrons this way. What would we have generated? So I do see CO2 as a possibility. What's the other piece? Carbanion. How stable is the carbanion? Not stable at all. Why do we not see the second carboxylic acid group eliminated? We don't have a stable intermediate to form. We don't have any way of temporarily stabilizing that carbanion. In our first case, we have that enol tautomerization that can allow us to stabilize the carbanion temporarily so that we can actually get that reaction to occur. Once the CO2's been kicked out, it's not like we can get that reversed because CO2 is a gas. Bubbles out of the reaction. We can't do anything about the reverse reaction. Okay? Questions about that? Okay. So, as an example of putting everything together, I tried to color this in so you could see the individual pieces. We're looking at the green boxes being the same pieces. Okay, so what we start off with is our strong base. That base will remove the hydrogen, our alpha hydrogen, making that carbon nucleophilic. That nucleophilic carbon can then perform a backside attack, kicking out our halogen leaving group. The intermediate is going to be this big, long, nasty, ugly looking structure. This is where you have to be careful. Why be careful? Most people would draw this. What's the issue with what I just have drawn? Missing a carbon. So really, really watch for those carbons. Okay, we need that extra carbon out there. Okay, there's our intermediate. What can we do now? We add the H3O+, which will hydrolyze our esters into carboxylic acids, and we'd have the diacid. If we give that just a little bit of heat, we can cause enough energy to break off one of those CO2s, and we end up with our final carboxylic acid product. Okay? So in the course of the reaction, what we've done is, again, added 2 carbons, 2 oxygens. It's always a good thing to draw over red letters with red pen. And our hydrogen out there as well. Okay, so we did a pretty substantial change in the overall structure by running the Malonic Ester synthesis. Okay. Questions? Okay. As I alluded to already, we could polyalkylate. So in the top case, we're doing a double alkylation. We're adding a red R group and a blue R group. Remember, to go through and do this, it has to be done in 2 separate stages. Okay, you can start with a strong base, add the R group. You've now generated an intermediate, intermediate product, I would venture as a guess is a better term, with our R group. Once that's on there, then we can react it a second time with a second batch of base and our new R group to go through and put on the second one. Okay? That is a common reaction. I've known plenty of professors to do that a whole bunch of different times. And now what we end up doing is adding on a bunch of extra carbons in that process. Okay? So kind of watch out for seeing big changes in your overall structure. If you see a lot of extra carbon groups, you're probably looking at a malonic ester synthesis, because it's really the only way you can get a whole bunch of extra carbons into a structure, particularly of different shapes and sizes. Okay? For some reason, and I don't quite understand why, they go through and call something the acetoacetic acid ester synthesis. As far as its chemistry goes, any ideas how different it is? Not really different at all. It's the exact same chemistry. Right? We still start with that relatively superacidic hydrogen. Why is it more acidic than, say, a ketone? You have both of those carbonyls contributing to removing that electron density. We can go through and put on an R group. We can go through and hydrolyze that to the carboxylic acid. Where are we? So if I wanted to cheat and be lazy with what's on there, just put that into a hydrogen. And we can still go through and add heat. We still will cause the elimination, okay? The loss of that CO2. Why can we still cause the CO2 elimination even though we don't have a carboxylic acid? I remember the malonic ester that we had an OH out there. Did that OH do anything? No. What we were concerned about was the chemistry of this carbonyl. It's the carbonyl that's really driving the loss of that CO2. We can take the electron density away, and it's this arrow, our purple arrow now, okay, that's the important one. That can occur because of the carbonyl. Okay, doing that resonance stabilization, pushing that negative charge, instead of being sitting on a carbon, sitting on that oxygen. That generates our enolate. The enolate can tautomerize back to the carbonyl, and we now have a ketone in our product as opposed to a carboxylic acid. Okay? Questions about that? Yeah.
Where's your R groups? Can you add two acid benzene rings? Or is that steric?
We're going to run into steric arguments with that. Okay? Just like with the alkylation that we talked about just previously, we're looking at primary R groups. Okay, our alkyl halides, our RXs. Where's a good place to write? Our RXs, that R group still needs to be primary.
So secondary carbon
Aren't going to work very well. What's the issue if you make it secondary? We said our alpha carbon can act as a nucleophile and a base. If you go through and make that R group secondary, what happens? Now you start to push the likelihood of an elimination reaction occurring instead. We really want to see that SN2 reaction. Though really the only way we can insist that an SN2 reaction is going to occur is if we use a primary alkyl halide. It is the only one that will push SN2. So you can go back and look at your SN1, SN2, E1, E2 dynamics. The only one that is characteristic for any one of those is actually the primary. As soon as it becomes secondary or tertiary, the other mechanisms show up as well.
How come in the lab we just did, it substituted on both sides with only one, but this one we have to add excess?
So here's the big question on that. In the lab, was it just a carbon electrophile? So our electrophile in this case is our Rx. What was our electrophile in the lab? It was a carbonyl. So we ended up making a more electrophilic carbon. That's what's happening with that change in the dynamics. Okay. Oh, this is another kind of summary slide on just that piece. Okay. So if we wanted to go through a mechanism, do you guys want to see a complete mechanism on this? I'm going to take that as a no. What was that, Josh? Probably. Probably see him. Okay. Let's address a couple issues first with this, and then we'll jump straight to the tautomerization process. Okay. So number one, we end up using a weaker base. Anybody notice any patterns? I guess we haven't looked at too many examples. Anybody notice something in particular interesting about the base that we chose to use in this case? Why ethoxide? Why is it not methoxide or propoxide? Does the ethoxide show up anywhere else? Shows up in our ester as well. The base that we use will match the ester functional group. Okay. The reason being, if we used methoxide, yes, we have a good base, but what else do we have? A good nucleophile. We can go through and react with the carbonyl instead. Okay. So we can't eliminate that reaction. The way we prevent us even worrying about it is that we make sure that we use the exact same piece. Okay. So that if indeed our ethoxide goes through and attacks that carbonyl, yes, we get a good leaving group and we kick out ethoxide. Well, we put on ethoxide, we kicked out ethoxide. It's the exact same. We don't have to worry about it. Which means while that reaction may be occurring, it doesn't do anything productive to change our products or our starting materials, so we don't really lose any products in the course of the reaction. What we're hoping for is the perhaps less frequent removal of that hydrogen to generate our enolate. All right, so we can actually look at our enolate in two cases. So we'll look at the first one here. Let's go ahead and remove that arrow drawing. So in this first case, what do we end up with? We have a nucleophilic carbon. How stable is a carbanion? Not stable at all. So if we try to just add a base to a standard alkyl compound, alkane, we're not going to see this form. It will never form. Why do we end up seeing it form in this case? We get a resonance stabilization. Okay. Put on our negative charge. Get that all sort of drawn out. All right, and what we've done is put that negative charge on that oxygen. In this case, what we are looking at is just resonance. Okay? And what we're trying to evaluate when we're talking about the tautomerization is what I would draw here in orange. The process of going back and forth between our neutral species and our carbonyl is the tautomerization. Did I spell that right? Or tautomerization reaction. We're taking advantage of that reaction by saying that that hydrogen is ultimately acidic. So that's really all the tautomerization is saying, is that we've made that conjugate base more stable. Okay? What we're evaluating is the relationship between our conjugate base and our starting acid, if you will. So that's all the tautomerization is talking about. The next issue with that tautomerization is then which way does the equilibrium lie? So all of our acid-base reactions are in equilibrium. We could draw out just a standard carbon compound. Okay, we could add a strong base, and we could remove that hydrogen. Okay, and one of the things that second semester is kind of all about is that everything is in equilibrium. Okay, so we generate that carbanion, and this reaction can go backwards and forwards. Which way does it favor?
The neutral.
The neutral one. So we see virtually no forward reaction. Okay, to the point where in first and most of second semester we would say there's not even a forward reaction. We only go back to our starting materials. Okay. Our tautomerization is just a special way of looking at and saying that that hydrogen on our alpha carbon is that much more acidic. Okay. And because it's now that much more acidic, we gave it a new name. We called it a tautomer, because there's a distinct relationship between those two structures. Okay. We take advantage of that to explain the acidity there, but we also take advantage of the tautomerization at the very end of this mechanism when we look at the loss of that CO2 group. Oh, that was ugly. Whatever. Okay. Oops. After we add our acid, we now have our carboxylic acid functional group. These electrons can swing across. And these electrons, let's leave them sit first on that carbon. What we end up generating is our CO2. And there's that ugliness. And that negatively charged carbon. Is carbon stable as a negative charge? No. So officially, we would predict that while this is in equilibrium, we would predict virtually none going forward and most of it going backwards. Okay? But what someone was able to notice is that we have the tautomerization relationship. Okay? We can stabilize that carbanion, which means instead of virtually none of it going forwards, nearly all of it goes forwards because we can stabilize the anion. So ultimately, the tautomerization is just a fancy way of saying make a stable carbanion. Okay? And that making a stable carbanion follows from a carbonyl. It's the carbonyl that's stabilizing it. Does that help explain it a little bit? So in both cases, it's still a carbanion. Both cases, we're still stabilizing it through a carbonyl. One case, it's having our species starting off as an acid. In the other case, it's starting it off as the malonic ester, or the acetoacetic ester type functional group.
So they're just showing stabilization of the negative.
Exactly right. Tautomerization is just about stabilizing that negative charge. And because it's that much more stable that we see this extra chemistry, they gave it a new name. Okay.
This is basically showing that that carbon wouldn't hold a negative charge as well as the oxygen would. So the tautomerization shows
Yeah.
stabilization of the oxygen will hold the negative over the carbon.
Yeah. Other questions? Okay. So we'll start into this a little bit. This last pseudo section is all around the carbonyl as an electrophile. So we'll see two types of reactions with our carbonyl as electrophile. We'll have aldol reactions, which you guys did in lab last week, and we're going to do Claisen reactions, which instead of it being a ketone, I think it's just that it's an ester. Okay? Again, the chemistry is still all the same. We just end up slightly changing the functional group, and since some other famous person happened to run that exact same chemistry about that same time, they got to add their name to it. Okay? So when we're looking at the carbonyl as an electrophile with our aldols, the original starting point was looking at the aldehyde and alcohol being in relationship with each other. Okay? So if we start with just this is ethylaldehyde, acetaldehyde. If we take two of those and we run it under the same basic conditions that we've been running in other cases, we note that those two aldehydes can react with each other, add with each other, and they form that product. Okay? When we look at that product, what functional groups do we have? We have the aldehyde. I swear that was blue. We have the aldehyde, and we have the alcohol functional group. Okay? So that's where that term aldol came from, was looking at solutions of aldehydes and noticed that we didn't have just the aldehyde. We had this other weird product where our aldehydes reacted with each other. Okay? And that's where they came up with the term our aldol reaction. Okay? A lot of this type of reaction is dependent on what base you're using. So if we use a really, really, really strong base, we don't have any reactive carbonyl. We don't have an electrophilic carbonyl. Why not? If we use a really, really strong base, what's the species that's present? It's only that species. Okay? Why does that get rid of our electrophilic carbon? Well, it's now resonance stabilized. Okay? So a really strong base prevents the aldehyde or the aldol reaction from occurring. If we use a weaker base, what happens? Well, if I have two molecules, one of them may have turned into the enolate, but the other one did not, which means I have a nucleophile and I still have some electrophile. It is now those two species reacting with each other to make the aldol product. Okay? So we take the negative, tack the positive, and we generate our product. Push some hydrogens around and we'd all be happy. Okay? So it's kind of the basics of what's happening with that. One of our carbonyls tautomerizes, the other one stays constant, and they now react as our nucleophile electrophile pairs. Okay?
Not
Yeah.
take the hydrogen off first? Why is it not take the hydrogen off and then tax the carbonyl? That makes sense. Like after you get like the step before the resonance makes the enolate, you get the negative carbon.
Yeah?
Why does that not act as a base and deprotonate the other aldehyde?
It could. What's the result?
It goes back to where you get a
If that acts as a base, what do we get? Call this structure A. This is structure or equivalent to structure A. We call this structure B. This one is equivalent to structure B. So yeah, it can act as a base, but what does that base do? As far as we're concerned, absolutely nothing, because we can't tell the difference between those carbons. Okay. So once we add a base and we start to set up this situation where we've formed some of the enolate and not a lot, we now have that potential for it to start to react and do interesting chemistry. So it could still act as a base, but it doesn't do anything productive. Okay? If it acts as a nucleophile, however, what ends up happening? We see now a pretty substantial change in the overall structure. Okay? And that's what's happening with our aldol. Okay? Which is a bit of a challenge when you go through and look at these reactions. You are starting to see that it's not just one reaction. There's 3 or 4 different reactions. All of them are occurring at the exact same time. Only one of them leads to something productive. What we're going to try and talk about in class is just the ones that lead to something productive. If you mention one, I'll go ahead and draw it up like we just did here. And what ends up happening? Nothing productive happened. And not even nothing productive, nothing actually changed. We couldn't even tell a difference between those structures. Okay? So, how would you figure that out? Draw it out and see what that difference is. After I drew it, yeah. Okay. So really what I would hope